You are welcome to the fifth session under Unit 6, and in this session, we're looking at azoles. So, at the end of the session, you should be able to name some examples of azoles, you should be able to explain the aromaticity in imidazole, you should be able to discuss the electrophilic substitution reactions that azoles undergo. So, quickly, we will look at the nomenclature, or the structure of these azoles. Now, azoles are five-membered heterocyclic compounds that contain two or more heteroatoms and at least one being nitrogen, right? So, at least one of the heteroatoms present is a nitrogen in the five-membered ring. So, we have purine, we have oxazole, we have imidazole, and we also have thiazole. Now, all these components or compounds we have here, all these are aromatic compounds because they obey the Huxley's rule of 4n plus 2 pi electron system. They are cyclic, they are planar as well. So, and then of course they are conjugated, right? So, all of these compounds here are aromatic compounds. Now, on the nomenclature, we've been talking about numbering. So I'm pretty sure numbering now is not a problem. So we always count or number with the heteroatom as number 1. So in the case where there are more than 2 heteroatoms, we give the priority to the oxygen followed by the sulfur and then before nitrogen. So when there's oxygen and nitrogen, we prioritize the oxygen as number 1. When there's sulfur and nitrogen, we prioritize the sulfur as number 1. And when there are 2 nitrogens, then we can look at the unsaturated nitrogen as our carbon number 1. So similarly, numbering is done such that the other heteroatoms give the least possible numbers, right? So please let's take note of that. These are some examples. We have 2-bromothiazole, we have 4-chloroxazole, we have 2,4-dimethyl imidazole as well. So we briefly look at imidazole. Now, imidazole has 3 pairs of localized pi electrons. I'm pretty sure as at this point we know which ones are delocalized and which ones are not. So, there are 6 pi electrons here and not 8 pi electrons for aromaticity. There are 6 because we need just 2, 4, 6 for aromaticity. We don't need one, this other one. So, we can see that this lone pair of electrons we have here are localized, whereas the lone pair of electrons here are delocalized. So the non-bonded electrons on the heteroatom number 1, the unsaturated nitrogen, are part of the pi cloud orbitals, whereas the lone pair of electrons found on our second tetraatom, which is N number 3, is sp2 hybridized, and the orbital is perpendicular to the pi cloud. So you realize that that is what we have here. So the N number 3 pi electrons are perpendicular to that of the N orbitals electrons found in the heteroatom number 1, right? So let's take note of that. Okay, so in considering the resonance energies, imidazole has a resonance energy of 14.0 kcal per mole, benzene is 36, whereas pyrrole is 21. So it implies that these two aromatic systems, that are benzene and pyrrole, are more stable than imidazole. So if you look at the resonance structures that are obtained for imidazole, so the resonance structures. Now, because there is a pair of non-bonded electrons that are not involved in resonance, imidazole can easily be protonated, right? So the pair of electrons on this nitrogen, which are not involved in aromaticity, are always available for protonation, right? So please take note. Okay, so with that being said, it justifies the reason why imidazole can exist in both the protonated and unprotonated form. So at high pH, you can have the unprotonated form. At low pH, you can have the protonated form. And this contributes to the importance of histidine, which is an important component in many enzymes, right? Of many enzymes. So imidazole, because of this unique property it has, it serves as a precursor in the biosynthesis of histidine. So in the human body, the protonated form can be found at some points, and the unprotonated form can also be found at some points. Now, the protonated and unprotonated forms of this imidazole have chemically different reactions they undergo, right? So the unprotonated form has essentially hydrophobic parts and aromatic characteristics, right? Whereas the protonated form is hydrophilic and positively charged. So please note these two, these two differences. Now, if you want to look at the electrophilic substitution reaction of imidazole, imidazole undergoes electrophilic substitution reactions at carbon number 4. So it is more reactive than pyridine, but less reactive than pyrrole towards electrophilic substitution reaction. So our imidazole is more reactive than pyridine. So please take note of that. That's if you are referring to electrophilic substitution reaction. So in the electrophilic substitution reaction, imidazole is more reactive than our pyridine, right? So let's note that. This is because the imidazole contains two different nitrogens, in which one exists with the properties of pyridine and the other exhibits the properties of pyrrole, right? So this is quite interesting. So at imidazole places itself in between the two. So imidazole is more reactive towards an electrophile than pyridine because of the two nitrogens it has. So at one point it's exhibiting the properties of a pyridine, at another point it's exhibiting the properties of pyrrole. Okay, so these are some examples. These are two examples of an electrophilic substitution reaction involving involving imidazole. Yeah.